So far in stats, we've been looking at single variable data. In this video, we're going to be focusing on bivariate data. This is where, unlike before, where we were only measuring one variable, we are now measuring two variables. Okay, so this is an example here where we have a list of 10 men and we have measured both the height and the weight of them, and these are plotted on this scatter graph here. Now, with bivariate data, we have two types of variables. We have the independent variable, or it's sometimes called the explanatory variable, and this is plotted on the x-axis. And we have the dependent variable, or it's sometimes called the response variable, and this is plotted on the y-axis. Okay. Now, there are quite a few definitions for these variables, and some people, and the textbook talks about this as well. It talks about that you control the independent variable and you measure the dependent variable. I personally don't like that definition, as for some examples it doesn't really work. The best definition, in my opinion, is the dependent variable depends on the independent variable. That is why it's called the dependent variable. Or if you want to think about this like explanatory and response, the response variable depends on the explanatory variable. So what does this actually mean? Okay, so let's look at this data here. So this data, on 10 different days, we have recorded the daily temperature and the number of ice creams sold by a particular ice cream shop on that day. Okay, and in this example, the temperature is the explanatory variable and the number of ice creams sold is the response variable, because the number of ice creams sold depends on the daily temperature, because the higher the temperature is, the more ice creams that you're going to sell. Okay, another example is this here, where we've recorded the total monthly rainfall in a particular month, and we've also recorded the number of floods in that month. And in this case, the monthly rainfall is the explanatory variable and the number of floods is the response variable, because the number of floods recorded depends on the total monthly rainfall. Okay, so correlation is the relationship between the two variables. Okay, now for a scatter graph, you need to define correlation using two things. You need to talk about how strong the correlation is, and you need to talk about the type of correlation, whether it's positive or negative. Okay, so let's go through some examples. So if we look at this one here, so we can see the points are going up, so this is a positive correlation, and we can see this is a very strong correlation, so this is a strong positive correlation. If we look at this one here, the points are going down, so this is a negative correlation, and we can also see this is a very strong correlation. So this is a strong negative correlation. Okay, if we look at this one, we can see the points broadly are going up, so this is a positive correlation, but it's not really as strong as it is up here. The points are kind of a bit more all over the place, so this is a weaker correlation. This is a weak positive correlation. Okay, if we look at this one down here, it's pretty much the same. The points are going down, so it's a negative correlation, but it's not as strong as it is up here, so this is a weak negative correlation. And then this one here in the middle, the points are completely all over the place, so here there is no correlation. Okay, something I just want to mention quickly is in this chapter we are only focusing on linear correlation. You can have other types of relationships. So for example, if you look at these points here, these points have an exponential relationship like this here, but we're not focusing on this in this chapter. These points here, we're only focusing on linear correlation. You would probably say that this has a weak positive correlation. Okay, we're going to talk about different types of correlation and non-linear correlation in year 2 chapter 1, but you don't need to know it for this chapter. Okay, so here's an example question where we're told a scatter graph is shown below, and the x-axis shows the ages of 20 people and the y-axis shows their results in a game based around reaction time, okay? And for part A, we need to describe the correlation between age and reaction time, okay? So for this scatter graph, we have the ages on the x-axis and we have their reaction times in milliseconds on the y-axis, okay? So we need to describe the correlation. So the way that we do this, we need to talk about how strong it is and the type of correlation. So if we start with the type of correlation, we can see the points are going up. So this is a positive correlation, and we can also see that this is a very strong correlation as well. I know we've got this point here that kind of breaks the correlation a bit, but it doesn't matter if you have 1 or 2 points. Most of the points are kind of along this line, so it's a strong positive correlation. Okay, and then for part B, we need to interpret our answer to part A in the context of the data. Now, they quite like to ask questions like this, where they ask you to describe what the correlation actually means. Don't overthink it, it's really simple. You just need to explain what it actually means when you have a strong positive correlation between age and reaction time. What this means is as age increases, reaction time increases. This is all that they're asking for, and that will give you the mark. So, as we've already talked about, correlation is the relationship between the two variables. Okay, now a causal relationship means a change in one variable causes a change in the other variable. And this is something people, not only at A-level maths, but also in the real world, get confused by. They think these two things are the same, which they're not. Just because you have correlation, that does not mean that you have causation, okay? So let's go through some examples to show how this works, okay? So this data here, in 10 days of the year, on the x-axis we have recorded the temperature on that day in a specific location, and we have recorded the number of people on a beach in that specific location, okay? So we're going to ask ourselves here two questions. Does this data have correlation and does it have causation? Okay, so let's start with correlation. So we can see that these data points are increasing, so therefore we have a positive correlation, so therefore we have correlation, okay? So do we have causation? Does the temperature increasing cause an increase of the number of people on the beach? And the answer is probably yes. We probably do have causation, because if you increase the temperature in that location, people will be more likely to go to the beach, and therefore the number of people on the beach will increase. So in this example, we have correlation and causation. Let's look at this example here. So this example, for 10 people, we have recorded their heights, and we've also recorded the number of times they visit the supermarket in a week, okay? So does this have correlation? Well, if you look at the data, you can see that the data points are increasing like this here. It's a pretty weak positive correlation, but we do have a correlation here. So do we have causation here? And the answer is no, because an increase in a person's height does not mean that that will increase the number of times they go to the supermarket in a week. The reason that we have got a positive correlation here is just completely by chance. There is actually no causation here between these two variables, and this is something that people get confused about a lot in real life. Is just because you have a correlation between two variables, it could be completely by chance. It doesn't necessarily mean that these two things are linked. If you have correlation, you can draw a line of best fit or a regression line. This is a straight line with equation y is equal to a plus bx, where a is the y-intercept and b is the gradient. If b is positive, then the line has a positive gradient and there's a positive correlation. So for example, if we had this graph down here, then this line could be y is equal to 6.02 plus 2.19x. A lot of the time regression lines will involve decimals. If b is negative, the line has a negative gradient and there's a negative correlation. So for example, if we had this graph down here, the line could be y is equal to 8.71 minus 0.56x. Okay, now the gradient of the regression line is quite important. The gradient means that when the x variable goes up by 1, the y variable goes up or down by b, depending on if it's positive or negative. So if we had this example here, when x goes up by 1, y goes up by 2.19, because this is the gradient. Now, an important note, if you are given bivariate data either as a scatter graph like this here or as a table, you will not need to find the line of regression or the equation of the regression line by yourself. It says on the specification you won't be asked that. They will give you the equation if you need it. Your calculator is actually able to find a regression line for bivariate data if you have it in a table. I'm not going to go through that here though, as you don't need to know it for your exams. Okay, so here's an example question where we're told the scatter graph below represents some data on the value of a car, which is the value of the car is the x-axis in hundreds of pounds, and the cost of its yearly MOT, which is the y-axis in pounds. And a regression line is shown with equation y is equal to 46.718 plus 0.105x, okay? And for part A, we need to use the regression line to estimate the yearly MOT cost for a car worth £12,500. Okay, so the way that we're going to do this, we're going to sub this value into this regression line in order to get an estimate. Now be careful, because the value of the car is in hundreds of pounds. So instead of 5,000 it's 50, instead of 10,000 it's 100, so therefore 12,500 here, x is going to be equal to 125. Okay, so this is what we're going to sub in as x, because it's in hundreds of pounds. Okay, so we're going to use this regression line, so it's y is equal to 46.718 plus 0.105, and then x, which is 125. And if you put this into your calculator, this is equal to 59.84. So this is an estimate for the price of the yearly MOT. Okay, so for part B, we're told John wants to use this data to estimate the yearly MOT cost for his car. The value of his car is 30 grand. We need to explain why this data is unsuitable for this estimate, okay? So this is unsuitable because of something called extrapolation. Okay, so extrapolation. So if we look at this regression line here, the maximum value of a car in this data comes up to here, which is 220, or because this is in hundreds of pounds, this is going to be £22,000. And the problem is this car is 30 grand, which is more than this. So in order to get an estimate for his yearly MOT cost, we would have to extrapolate this line to here, for example, in order to get this data value. And the problem is this regression line has been calculated for this range of data. Over here, this regression line might not work because we don't know, because it's outside this range of data, okay? And this is what extrapolation is. If we're trying to find a value inside this data range, this is called interpolation. But here we're doing extrapolation, so this is why it's unsuitable for this estimate. So it's extrapolation, so say something like the value is outside the data range so the estimate may be less accurate, and that will give you the mark.